I want to just finish off one more Green's theorem just to kind of tidy up the process. And then we'll move on to our next section, chapter 16.5. That won't be in the test, but it will be next week's. Okay, so we've got a closed loop C, line integral. C is made up of this. So the first thing I'm going to do is draw what that looks like so I can figure out what D is going to be, our area. Okay, I'm pretty sure I got a picture of this somewhere, but anyway. 9 minus x squared looks like that. And 0, 9 is here. And 3, 0 is here. Okay, so that's this piece. If you go from 0, 0 to 3, that's 3 there. You go on this guy. And I got my arrows wrong. You're going that way. You're going this way. And then you're coming down here. Okay, that makes sense. So we are going that way. So it's positive orientation. I'll put this in blue because it looks like an X. This is the way we're going based on that information. So we should be able to put this package together. That line integral is going to be a double integral over D, which is that region there. And it's going to be that guy. dA. That's going to be the double integral. If you differentiate, I hear the function. This guy's P and this guy's Q. Oh, come on. Don't do that to me. No, don't do that. Oh. Based on what I've got here, do you know what the answer is going to be? Why am I kind of annoyed at it?
It's going to be 0?
Yeah, which means I don't need to do anything. Okay, let's pick a different version. Can I make that y squared so I don't have 0? Because I want to do the whole thing, right? So I've changed it. It's now quite different from 10. And so we're going to do differentiate this guy, you get 2y. Differentiate this, you get 1 there. That's much nicer. And D is going to be this region. And I do my usual vertical strip because I like that one. This guy is going to be from x equals 0 to 3, and y is going to be 0 to 9 minus x squared, which is what that curve was. So I've got all the pieces I need. It's going to be y equals 0 to 9 take away x squared. It's going to be x equals 0 to 3. There's my guide. Going to do the y first. Going to do the x second. And I'll just dot that. Would you agree that once you set it up, it's just a good old-fashioned double integral, not separable. So you'd integrate that and get y squared minus y, plug these two guys in, get the answer in terms of x, and then integrate with respect to x from 0 to 3. And that's the end of Green's theorem. It's a really nice little niche market. It basically says, if you want to find the integral of a closed loop, and it's not necessarily a conservative field, then you can turn it into a double integral, in particular this double integral. And the area of the answer to this is the same as the line integral. So who's the new guy in Thur? This guy. Curls and divs. I'm going to show you a little video to try and visualize what the heck these things are. But let's talk about how to calculate them first, and then we'll go and show you that video. The curl of f is a vector. It's a three-dimensional vector. So you do curls in 3, 4, 5 dimensions and so on, but we'll only do it in 3. And the curl of f is ijk, an operator, the partial derivative with respect to x, the partial derivative with respect to y, and the partial derivative with respect to z. We call these operators in the sense that they're not on their own anything except something that you're going to do to somebody else. They operate on, in particular, this guy. So if you think of f as being your classic three-dimensional vector field, where p, q, and r are functions of x, y, and z, then the curl of f is this fella. Now, you have seen these. Can you remember how to do cross products? Right. Right. So this is going to be a cross product, but normally in cross products you have numbers like 1, 2, 3, 5, 6, 7, right? But we'll show you how you do the cross product. That's what this is, and it's going to generate a vector when it's finished called the curl vector. And then there's got this guy down here, which is the div of f. And div, if you do it in terms of operator notation, it's the delta dot product with f. So that's what it looks like. So let me show you an example of that. Let's take a function, a nice vector function, vector field, 3x plus y squared plus x, and x, y, z. Nothing particularly interesting about it. It's a vector field. If you wanted to find the divergence, that's div of f for short, the divergence of this f, it's the partial derivative of this guy, p, with respect to x, plus this guy, just q, this guy's a, so this guy, and this guy. So let's see what we get. If you differentiate this with respect to x, you get 3. If you differentiate this with respect to y, you get 2y. And if you differentiate this with respect to z, you get xy. And it's as simple as that. So the divergence of f is this expression. Now, do you notice that is not a vector, right? It's just an expression, right? It's essentially a one-dimensional object. Now, to calculate the curl of f, that's much messier. So you do an ijk. You put in the operators, the partial derivative with x, with y, and with z. And then you put in p, q, and r. So in this case, p is going to be that guy. Q is going to be that guy. And r is going to be that guy. And the curl of f is the determinant of this 3 by 3. So it's so many i's, take away so many j's, plus so many k's. Now I'm doing right now, just by sheer coincidence, my calc 3. And my calc 3 are finding these guys called the cross product, right? ijk, ijk. Do you notice that middle one is always subtract as part of the process? Now, normally what you would do, and we're going to do the same thing, is if you want to know the term that goes here, you cover up the I and you get this guy. Now, you usually would go multiply those two and take away them, right? Major diagonal, take away minor. We are going to do that, but it's going to be a little bit different. It's the partial derivative of y, of that guy, take away the partial derivative of z of this guy. So it's not a multiplication. Do you see this as an operator? I'm doing a partial derivative with respect to y of whatever's here. Take away the partial derivative with respect to z of what's going here, and that's this guy. So let's see what that gets us. If you do the partial derivative of x, y, z with respect to y, you get xz. If you do the partial derivative of this with respect to z, you get 0. And that just becomes xz. Right, the middle one, cover the middle up. The partial derivative, major diagonal, is the partial derivative with respect to x of x, y, z. Take away the partial derivative with respect to z of 3x. I can't even write it down there. So take away. If you differentiate this guy with respect to x, you get yz. Take away the derivative of this guy with respect to z, which is 0. And minus that guy gets you minus yz. And last but not least, this fella at the end. Major diagonal gets you the derivative of, with respect to x, of y squared plus x. Take away this guy, which is the partial derivative with y of 3x plus y. Let's see what that gets me then. If you differentiate this with respect to x, you get 1. If you differentiate this with respect to y, you also get 1. So that ends up being 0. So the curl of f is the vector xz, comma, negative yz, comma 0. And that's the guy we call the curl. So you have to get comfortable and familiar with finding the cross product of this operator with that function, which is what that is saying. Operator cross product with f. The divergence is operator dot product with f. So if you ever wondered why you would want to do cross and dot products, here's an advanced reason. Okay, that's 1. I don't think 1 is enough. So let's do another one. Let's suppose my function is x squared yz, yz, z cubed plus x. That's p, that's q, and that's r. Going to find the divergence of f first. So that's the partial derivative of p with respect to x, plus the partial derivative of q with respect to y, plus the partial derivative of r with respect to z. If you do this with x, you get 2xy. If you do this with y, you get a z. If you do this with a z, you get 3z squared, and you are pretty much finished. Nothing here adds or combines, so I'll just leave it. Now you want to get the curl. That's going to be this. That's going to be the fun one. It's I, j, k. The operators are dx, dy, dz, and p, q, r go here. So it's going to be x squared yz, yz, and z cubed plus x. So this is going to be so many i's, take away so many j's, plus so many k's. And this time I'm just going to do them in my head. Okay. If you do the major diagonal, you're finding the derivative of this with respect to y, which is just 0. Take away the partial derivative with respect to z of this term, which gets you y. If you do the middle one, With respect to x, you get 1. Take away with respect to z, you get x squared y. Last one. With respect to x, that term gets you nothing. Take away with respect to y, that term gets you x squared z. Tidy that up. The negative of all this is a bit messy, but you get that. And tidy this one up, you get that. So the div of f is that scalar, and the curl of f is this vector. Now you might think, what are you doing, or what are you getting out of doing those two operations? I mean, because right now it's just mechanical, right? You're saying, here's a formula. This is how you get a thing called the divergence of f. This is how you get a thing called the curve of f. These are calculations done on a vector field, and they tell you a lot about what the heck is going on in that vector field. And here is a little video. It's quite a long video. I'm not going to show you all, but it is kind of cool, and it gives you the gist of what's going on. And let's see if I can share sound. First, are you looking at a video?
Yes.
Great. So I'm going to click on this video and make
Today,
it big.
you and I are going to get into divergence and curl. To make sure we're all on the same page, let's begin by talking about vector fields. Essentially, a vector field is what you get if you associate each point in space with a vector, some magnitude and direction. Maybe those vectors represent the velocities of particles of fluid at each point in space, or maybe they represent the force of gravity at many different points in space, or maybe a magnetic field strength. Quick note on drawing these, often if you were to draw the vectors to scale, the longer ones end up just cluttering up the whole thing. So it's common to basically lie a little and artificially shorten ones that are too long, maybe using color to give some vague sense of length. Now in principle, vector fields in physics might change over time. In almost all real-world fluid flow, the velocities of particles in a given region of space will change over time in response to the surrounding context. Wind is not a constant, it comes in gusts. An electric field changes as the charged particles characterizing it move around. But here, we'll just be looking at static vector fields, which maybe you think of as describing a steady-state system. Also, while such vectors could in principle be three-dimensional, or even higher, we're just going to be looking at 2 dimensions. An important idea, which regularly goes unsaid, is that you can often understand a vector field which represents one physical phenomenon better by imagining what if it represented a different physical phenomenon? What if these vectors describing gravitational force instead defined a fluid flow? What would that flow look like? And what can the properties of that flow tell us about the original gravitational force? And what if the vectors defining a fluid flow were thought of as describing the downhill direction of a certain hill? Does such a hill even exist? And if so, what does it tell us about the original flow? These sorts of questions can be surprisingly helpful. For example, the ideas of divergence and curl are particularly viscerally understood when the vector field is thought of as representing fluid flow, even if the field you're looking at is really meant to describe something else, like an electric field. Here, take a look at this vector field, and think of each vector as describing the velocity of a fluid at that point. Notice that when you do this, that fluid behaves in a very strange, non-physical way. Around some points, like these ones, the fluid seems to just spring into existence from nothingness, as if there's some kind of source there. Some other points act more like sinks, where the fluid seems to disappear into nothingness. The divergence of a vector field at a particular point of the plane tells you how much this imagined fluid tends to flow out of or into small regions near it. For example, the divergence of our vector field, evaluated at all of those points that act like sources, will give a positive number. And it doesn't just have to be that all of the fluid is flowing away from that point. The divergence would also be positive if it was just that the fluid coming into it from one direction was slower than the flow coming out of it in another direction, since that would still insinuate a certain spontaneous generation. Now on the flip side, if in a small region around a point there seems to be more fluid flowing into it than out of it, the divergence at that point would be a negative number. Remember, this vector field is really a function that takes in two-dimensional inputs and spits out two-dimensional outputs. The divergence of that vector field gives you a new function, one that takes in a single 2D point as its input, but its output depends on the behavior of the field in a small neighborhood around that point. In this way, it's analogous to a derivative, and that output is just a single number, measuring how much that point acts as a source or a sink. I'm purposefully delaying discussion of computations here. The understanding for what it represents is more important. Notice, this means that for an actual physical fluid, like water, rather than some imagined one used to illustrate an arbitrary vector field, then if that fluid is incompressible, the velocity vector field must have a divergence of 0 everywhere. That's an important constraint on what kinds of vector fields could solve real-world fluid flow problems. For the curl at a given point, you also think about the fluid flow around it, but this time you ask how much that fluid tends to rotate around the point. As in, if you were to drop a twig in the fluid at that point, somehow fixing its center in place, would it tend to spin around? Regions where that rotation is clockwise are said to have positive curl, and regions where it's counterclockwise have negative curl. And it doesn't have to be that all of the vectors around the input are pointing counterclockwise or all of them are pointing clockwise. A point inside a region like this one, for example, would also have non-zero curl, since the flow is slow at the bottom, but quick up top, resulting in a net clockwise influence. And really, true proper curl is a three-dimensional idea, one where you associate each point in 3D space with a new vector characterizing the rotation around that point according to a certain right-hand rule. And I have plenty of content.
Oh, I like that video. It's hard to imagine what you're calculating, right? So at least you've got a kind of idea of what these two things are. So let's take this vector field in 3D and let's just choose a random point in 3D space. Let's choose the point 1, 2, 3, right? If I plug it into the divergence, the answer I get is 2 times 1 times 2 plus 3 plus 3 times 3 squared. And that's what, 4, 5, 6, 7. 7 and 27 is 34. That is a positive number. So in 3D space, isn't that point in space spewing out stuff, right? The vectors are more leaving it than coming into it, right? Now, if I calculate the curl at F, I'm going to get negative y, which is negative 2, negative 1 plus that guy squared times that, which is 3, so that's 2. And this fella here is negative 1 squared times 3 is negative 3. So what I'm getting here is that if you imagine that point in space, the net effect of everything that's coming in and everything that's going out, the net effect is this vector. So if you combined all the pieces coming in and all the pieces going out, that's a vector. Can you think of that as being the direction the wind is blowing? So you've got your atmosphere with vortexes and, right, you know, swirls of air, and some air because it's cold coming down and some air that's hot that's going up. But the net effect in this particular one is that at that one point in time, there's a single vector that's saying that it's pointing that away. Now, if you did that for all of the things, wouldn't you get a vector field? And wouldn't you now be looking at a vector field in a way that would be telling you what the wind is doing in a big picture, rather than just at one specific point? For instance, in the center of a cyclone, right? You know, the big swirly things. at the center of a cyclone, what do you think the curl would be? Zero, unless the cyclone's got a little bit off looked. But don't cyclones move? And the reason they move is that that curl might not be quite zero. Couldn't it be a little bit pointing westy, in which the cyclone will now move west? Now, in a perfect cyclone, it would be zero, wouldn't it? It'd just swirl around in a big circle and not budge. But can you imagine outside that cyclone, there's extra wind moving it, pushing it westward. And so when they model weather patterns, for instance, can you see why having these types of calculations, all done by computer, by the way, because they are so difficult and there's so many of them, that they can model not only what directions the cyclone going to go, but can't they also measure how strong it's going to go and how fast it's going to go? Because if this vector is really big, isn't it traveling fast? And if this vector is considered, no, the magnitude, I should say, right? If it's a big magnitude, isn't it shooting fast westwards? And if it's very small magnitude, it's, you know, plodding along quite slowly. So you got an awful lot of imagination, you know, information from the div and the curl, right? So have I convinced you that it's worth doing, right? They can be, come on, Tessa, they are worth doing. They're cool. Don't depress me like that. That's not nice of you. I think they're worth doing, and I'm not an engineer. And so if something like that makes me think, then I am cool. So
I honestly can't think of a modern technology that wouldn't be using some application of these maths.
that's the kind of information that lots of things would probably want to deal with. Right. Okay, now, conservation, a conservation field, right? Conservative field, I should say. We know the test when it's a 2D guy, don't we? Can you remember what the test was? Remember that one? Okay. We can now do the test for a conservative field in 3D. If the curl of F is the zero vector, right? 0, 0, 0, you have a conservative field. Don't we like conservative fields? Because conservative fields, they allow us to do line integrals, don't they? Because all you need to worry about is where does it start and where does it finish? And that's a pretty important shortcut to be able to do. So the questions that we're going to deal with are find curls and divs, and occasionally, at least for today, after we find curls and divs, to see whether something is a conservative field or not. So here is our first question. Our vector field F is described as x, y squared, z squared, comma, x squared, y, z squared, comma, x squared, y squared, z. Would you agree that that vector field has some kind of symmetry thing going on? I mean, it's not perfect symmetry, but there is a kind of symmetry going on. Do you think that's going to be a conservative field? What do you think? Do you think that might be? things that have a lot of symmetry to them tend to be conservative fields. Not all of them, there's exceptions to everything, but the vast majority will be. Let's find the curl then. So we go I, we go J, we go K. We put in the operators, and then we put in P, Q, and I. Are you comfortable about setting this up? Are you happy about where all the bits go? Yeah. Then it's going to be so many I's, take away so many J's, plus so many K's.
You accidentally put an extra x squared
Oops,
on the.
Okay, well cut. That's just X. Well cut. Right. So cover up that guy. The major diagonal. Differentiate this with respect to Y, and you get 2x squared YZ. Take away minor diagonal. If you differentiate this with respect to Z, you get 2x squared YZ, which is 0. Okay, move to the middle one. Major diagonal, if you differentiate this guy with respect to X,
Wait, why is it 0? Oh, okay, I see. No, never mind.
Okay. You differentiate this with respect to X, you get 2x y squared Z. Take away 2x y squared Z, which is 0. Last one. If you go this way, you get, with respect to X, you get 2xyz squared. Take away, if you do this with respect to Y, you get 2xyz squared, which is also 0. And our prediction was correct. Isn't the curl of this vector field 0, 0, 0? And so according to the guy that we talked about, isn't this a situation where there is no tendency for the thing to turn at all? There is no little eddies and waves. It's basically fixed, right? Nothing changes. Now, the div, I always find the div easy to do, because you just differentiate this guy with respect to X, add the second one, that's this guy with respect to Y, and add the third one with respect to Z. And if you do this one with respect to X, you get Y squared, Z squared. If you do this one with respect to Y, you get X squared, Z squared. And if you do this one with respect to Z, you get X squared, Y squared. And even although I do not have any specific point, would you agree that no matter what X, Y, and Z I choose, with the exception of the origin, won't this always be positive? So in this part of the universe where this vector field exists, isn't every single point a source? Things are leaving, right? Coming out of it, right? Becoming, That's probably what the Big Bang looks like, right? When the Big Bang happened, wouldn't there be every single point in space would be spewing out stuff going outwards, right? There'd be nothing going in. So I can imagine that happening. Okay, let me pause for a minute. Are you getting a little bit more comfortable of just the mechanics of calculating a curl and a div? We're not doing anything much except maybe occasionally saying this is a conservative field because we know that's what you get. Getting lots of nods, so I'm happy with that. Let's try another one then. This is question 2. I don't normally write this down, but I am going to write it down the way that they've written it. They seem to like IJs and Ks a lot. I don't like IJs and Ks because when I see that, you know, it's very, you know, how careless I am at the best of times. Even if a question starts off life looking like that, isn't it, well, I'm trying to sell this. In my opinion, isn't that much easier to tell who P, Q, and R are when you write it like this than when you write it like that?
Oh, heck yes.
Okay. So why don't you just, if that helps, why don't you do that for all your questions? They might be written like that, but write this down instead. I'll do the divergence one first. So if you differentiate this with respect to x, you get 7y e to the z, plus if you differentiate that, well, you get nothing. And if you differentiate this with respect to z, you get y e to the x. And so not really anything as far as style points go. I guess I could pull out a y. I'm not sure it's worth the effort, but I've done it now. There would be your answer. Feeling good? Now, I actually think this question is going to be easy. And the reason why I think this is going to be easier than normal, whenever you get a 0, doesn't that tend to help this thing? You know, because there's a lot of zeros floating about. So let's figure out what it is. Curl of f then is going to be ij and k. Our operators. And we're going to have a 7xy e to the z 0 and a yz e to the x. It's going to be so many i's, take away so many j's, plus so many k's. So cover this guy up. If you differentiate this guy with respect to y, you get z e to the x, take away nothing. So z e to the x, come on. If you do the middle one, you're going to get, you're going to get yz e to the x, and take away this guy, minus 7xy e to the z. Not very pretty. And if you do the last one, you're going to get nothing. Take away, if you differentiate this fella with respect to y, you get 7x e to the z. And nothing very interesting about it. It was actually a little bit longer than I thought it was going to be, but that's fine. Any questions? So if div is positive, stuff is coming out, right, spontaneously popping out like a white hole. And if div is negative, isn't that stuff going in? Which is just like a black hole. I think that makes sense. Can you imagine the universe just was made up of black holes and white holes? Right? And matter, just, you know, not planets, but just matter floating about, right? Dust and so on. The div would be able to tell you where all the black holes are and where all the white holes are, right? You could at least analyze them in that sense. And the curl, Oh, that would work. Don't galaxies rotate? Spiral galaxies rotate. I know they take a long time to do it. Isn't the curl telling you how it's rotating? I mean, it might be over 1 billion years, but yeah, I like that one.